Hello, in this lecture we shall see the types of doubling machines that are there. We have already learned a few things in the first lecture. So we shall go ahead and see what is the other method of applying or doubling. So let us first see the principles that are these machines are based on, doubling principles. The doubling machines are based on either one of the following two principles, that is down twisting or 2-4-1 twisting. So basically you will find these two principles that are used for doubling. There is one more type, that is up twisting principle, but it was used specifically for doubling of silk and filament yarns. So in this lecture we will see the first two popular types that are there. Sometimes even ring frame was modified to be used as a ring doubler by replacing the drafting system and the creel on the ring frame. So there are other alternative methods of obtaining a double yarn. We know already all this. It is already discussed in alternative spinning systems, where we have learned twist spinning, which is cyrospun or duospun, self twisting, that is rubbing technique, as well as ply fill, which is a false twist process. And that have these three are alternative methods to obtain a double yarn, but we know that they have a limited application. So let us just refresh our memory on down twisting. A part of this we have already studied in lecture 1, where we have a assembly wound package. The feed rollers, using any style of dry or wet doubling, is going to feed the yarns that are to be plied further, and it will be wound, twisted and wound onto a double flanged bobbin with the help of a ring and traveler system. So this was the normal passage. The yarns are withdrawn from the supply package by the feed rollers and are twisted by the ring and traveler before being wound on a double flanged bobbin. To produce a cabled yarn, so to produce a yarn which is a cabled one, we need to have one more step here. The output of this process, that is this doubled yarn on the double flange bobbin, may be again doubled to get a cabled yarn, and the passage would look like this. We have two double flange bobbins, that is these are two doubled yarns which are again passed through the system to get a cabled yarn. So having seen this basic conventional way of producing a doubled or applied yarn, let us see one more method, which is known as a 2-4-1 twister, or in short TFO. With the 2-4-1 twisting system, the thread obtains two turns with one revolution of the spindle. So normally in the earlier system, where one rotation of the traveler would insert one twist into the yarn, here it is inserting two turns for one revolution of the spindle. So this is highly productive when you compare to the conventional system. The TFO twisters are gaining worldwide acceptance in both spun yarn and filament yarn sectors, mainly because of its inherent advantages like production of a long length of knot-free yarns of two or more ply, which facilitates better performance in the subsequent processes by inserting twist and winding on a suitable package. So here the package size is also, we can have directly a cone or a cheese, and the production is higher, so that is the advantage. And yeah, of course, higher productivity, and the number of spindles per TFO twister, it varies widely from 88 to 280, the most popular being 144 spindles. So the machines generally that one might find in the mill is having around this range, and popularly 144 spindles one might find. So having seen a little bit about or understood how a TFO inserts two twists for one revolution of the spindle, details we will see later. First, let us have a basic look of how the machine is. So we'll see this video. Okay, so having seen this video, now let us look at the passage of yarn through a TF4 or 241 twister. Um, so we can see here there is a spindle. On the spindle, the supply yarn is there, um, in the which is known as a cheese pot here. This is the protection pot that is there outside. This is the flyer which was rotating, as you have seen in the video, which was rotating at the top, and this is the hollow spindle. This is the spindle brake. If you want to stop the spindle for piecing or any other purpose, this is the brake that is applied. Then this is the, of course, the spelling BRAKE should be over here. And then you have this, whatever yarn is going to come out after twisting is going to be led through the thread guide, through the take up roller, through the grooved drum, and what you get is the final plied and twisted yarn wound on cheese. So let us see how this actually works. The required number of yarn packages, assembly wound yarn on the cheese, are creeled on the hollow spindle of the protection pot. As I've already said, this is the assembly wound package which is there on the spindle, hollow spindle in the protection pot. The thread is drawn from the package through a guide mounted on the freely rotating flyer and fed through the hollow spindle. So the yarn would be taken out from this particular assembly wound package, and through the flyer it will go into the hollow spindle. Uh, and fed to the hollow spindle in the protection pot with the help of a nylon wire. We'll see how this is threading is done later on. How this yarn is passed through the hollow spindle right up to the bottom here. The yarn is taken out from the bottom of the hollow spindle, forming a balloon. So we will have yarn coming out of the bottom, and it forms a yarn balloon. The yarn is then passed through the guide to the winding head. So the yarn will then go to the winding head through this particular guide. So this is the passage. Each rotation of the spindle will insert one turn of twist in the length of the yarn within the spindle, plus another turn of twist in the yarn balloon. So these are the two places where the twists are inserted one by one, and two twists are inserted while they pass through this particular passage. We'll see it in details. As a result, two turns of twist are inserted into the yarn for each rotation of the spindle, hence the name 2 for 1 twister. So this is a sort of sketch which will clarify as to where the two twists are inserted. Twisting, that is the first, the feed yarn undergoes a first twist between its entry into and exit from the spindle. So this is the location where it will first enter, the yarn will enter, and the second location where it will exit from the bottom of the spindle. This is the first path where the first twist is inserted, and a second turn is given in the outer balloon between the spindle and the pigtail thread guide. So your next twist, the second twist is inserted between this particular exit at the spindle and between the pigtail thread guide. So the first twist is inserted in this area, and the second one is inserted in this region. So this is how two turns of twist are inserted in TFO. So the number of twists inserted. To obtain the 2 for 1 effect, the pot with the untwisted feed package is kept motionless on the spindle rotor by permanent magnets. The pot does not rotate anywhere. We have seen that in the video also. The pot is stationary and they are kept motionless on the spindle. So the number of twists or twists per meter is calculated by spindle speed and RPM into 2, because we are inserting 2 twists per spindle rotation, and divided by yarn length in meters per minute. So we can calculate number of turns per meter. Creeling. The stationary supply package, that is the assembled yarn package, is fed to the TFO frame in the protection pot, which is also known as a cheese pot. The hollow spindle in the protection pot rotates to impart the twist. The spindle is rotating. The pot is stationary. The protection pot. The protection pot is provided to prevent interference of unwinding yarn with the ballooning yarn. So we are having one yarn which is unwinding from the package, and the other yarn which will form the balloon outside the pot. And the pot is going to prevent the interference of these two yarns, or they're touching each other or getting entangled and breaking. So the protection pot is provided to prevent this interference. It remains stationary because of the magnetic force while the spindle is rotating. When the spindle is rotating, it might tend to rotate along with it. So to keep it stationary, we are using magnetic force. The magnets have been fixed in the holder radially outside. So outside and inside the pot, the magnets are fixed, and they are fixed in such a way that the unlike poles are facing each other, and that is why, since they are attracting each other, it will avoid or prevent the pot from rotation. It houses a cylindrical stationary feed package and provides support at the time of unwinding of yarn from the package during working. So this is the pot which provides support during unwinding. So this is the image of the cheese pots in the machine. The protection pot called cheese pot around the package also protects the feed package from damage, abrasion, dust and fly. So other than providing this kind of support or preventing interference, it also provides some sort of protection to the feed package from any kind of abrasion, dust and fly. So function of the pot and its size. The main objective of the providing protection pot are to protect the feed package from damage, facilitate startup of the balloon, separate the balloon and the feed yarn to avoid abrasion, and also to protect the feed yarn from dust and fly. So this we have already seen. This is just a summary. Normally the diameter of the protection pot depends on the diameter of the feed package. So closer the internal diameter or protection pot to the outside diameter of the feed package. That means if the diameters are somewhat similar, that means the protection pot is just larger than the feed package. It is always better because it will lead to a saving in a space. So it leads to better space utilization percentage for the particular type of machine. So we can accommodate more packages along the length of the machine if the pot was just exactly or just slightly bigger than the feed package. So it will always the pot diameter will be dependent on the feed package diameter. Pot sizes used by the mill range from 120 mm to 220 mm, whereas 150 mm is the most popular package or the pot size. The weight of the feed package is normally decided by delivery package weight and pot diameter of the 241 twister. The weight of the feed package varies widely, very widely between mills in all the counts, ranging from 475 grams to 1890. So for coarse counts, maybe this is it goes to the higher weights, and for fine counts it may go to 475 grams or so. In cotton counts, up to 2 by 40 is the most popularly used feed package weight is 945 grams. This is just an indicator for you to understand the ranges and the weights that these packages come in. So we come to the next part on the machine, that is the flyer. So this is the flyer which can be clearly seen here. Tension variator with flyer. So there is a tension variator along with the flyer. The assembled yarn passes through the flyer and the tension variator, which imparts requisite twist and tension needed to form the yarn package. So tension mark on the tension variator. This is the tension variator where we can see a number 4 marked over here. This is the flyer. Tension variators have a marking number to use the suitable tension variator according to the count of the yarn. So this number can be varied as per the count of the yarn and the tension required in the yarn as per our need. So yarn passage to wind after twisting. So this is how the yarn goes. This is the yarn balloon that is formed outside over here and inside also. Inside, the way we have seen the passage already, and once the yarn comes out from the bottom of the spindle, it forms a yarn balloon outside like this. Then it will further go on to the final winding. So hollow spindle and the threading. So this is the spindle in the cheese pot. This is the base, how it looks. This is the point where the yarn will come out. This is the entire spindle, the way it looks. The assembly wound yarn or cheese is mounted on this hollow spindle, um, and the threading of it, or rather how to insert the yarn, this is how it is done in steps. First, the nylon wire is inserted. It's a stiff wire which is inserted into the hollow spindle from top to bottom, and then the top end of the wire is the yarn is tied with it. The yarn from the package is taken out and it's tied with the end of that nylon wire, and then finally from the bottom that nylon wire is pulled out, and along with it whatever tied that yarn we have tied, it will come out from the bottom of the spindle, taking out the thread from the bottom of the spindle. This is how in 3 steps we can thread the yarn from the top of the spindle to the bottom. Then we come to reserve disc and the yarn break. Let us see what that is. Um, just to understand the image, this image better, this is the place where we have already seen where from the top of the spindle and the bottom, the first twist is inserted, which is shown here. Because this acts like a top of the spindle acts like a grip here, and this is rotating spindle. So it will insert the first twist, and the second twist is inserted between the bottom of the spindle to the guide that is there over here. This guide here acts as the uh, grip, and since this bottom is the spindle is rotating, it will insert the second twist into the yarn. So let us see the what is meant by spindle rotor. It consists of spindle blade, steel bore, reserve disc, and bearing assembly. This entire ceramic guides are also mounted wherever necessary. This entire assembly is called as a spindle rotor. Internal thread brake. The untwisted yarn passes through the entry pipe, then through the internal thread brake. We've seen that it is going through the tensioner, so the yarn holding assembly, and thereby it is pressed between capsules and ceramic bushes inside the spindle. This tensioning device is adjustable in multiple steps. It influences the internal inner delivery tension and does the reserve around the reserve disc on the rotor. So there is some reserve here at the bottom. This is known as a storage disk. Some reserve is kept over here. We'll see the importance of it shortly. So it will this particular tension will also influence the amount of yarn that is reserved on the disk. The capsule, that is the tensioner, has its highest braking effect in position 4 and lowest in position 1. So 1 to 4 can be adjusted. In the earlier slide in the image we saw the position 4 was kept, which had the higher braking effect. So a sufficient reserve is absolutely necessary to achieve optimum results on a 2 for 1 spindle. That is, in such cases, sufficient reserve or storage at the bottom is necessary. Amount of thread around the reserve disc of rotor would be around 1.5 to 2 turns with full feed package. The reserve must be at least half round when the package is empty. So in the beginning of the package start, it will be around 2 turns, and later on this reserve can be reduced to around at least half a round should be there on when the package is almost nearing the or getting empty. This can be achieved by adjusting the feed package tension or unwinding tension slightly and adjusting the capsule and tension variator system. Internal thread brake in connection with the flyer weights. So we can adjust this by changing this tension. The reserve can be changed. It will depend on the spindle speed, yarn count, inserted twist, and the frictional resistance of the yarn. So there is a facility to change this tension. So importance of reserve on the reserve disc. In TFO twisting, twisting is introduced in two stages, and the yarn from its unwinding stage to the twisted stage will have a wider path in untwisted, semi-twisted, and fully twisted stages. That means we have seen the passage, and it is the path is longer than that is normally there on a doubler. In a normal doubler, whatever yarn is coming from the package, assembly wound package, it is directly coming out and twisted immediately, whereas in this case it has to pass through the hollow spindle the entire length, come out from the bottom, and again it will come out in the form of a balloon, and then it will get finally fully twisted. So there are three states in which the yarn exists. That is untwisted, which is there on the package, then semi-twisted, which is there in the spindle, and as soon as it comes out from bottom of the spindle till it is fully twisted. So there are three stages which the yarn goes through, and the path is longer. The variation in the reserve and the reserve disc will increase or decrease the path of the yarn in half twisted range. So if we increase or decrease, it basically affects the yarn that is there inside the spindle. This contributes to the variation and twist in the yarn at the semi-twisted stage. Semi-twisted stage means the yarn which is twisted in which is there in the spindle. If the reserve is excessively more than the recommended reserve, the long wrappings of the yarn along the reserve disc will introduce a tendency of semi-twisted yarn to untwist in that path, and therefore before it enters the balloon area. So some amount of twist will be untwisted if too much of a reserve is there on the disc. In the balloon area, the yarn is rotated by means of air drag. The amount of twist that is introduced in the yarn due to ballooning will have the possibility of flowing back to the yarn in the reserve if there is any variation in the balloon conditions in the reserve area. So whatever balloon conditions are there, along any changes, kind of tension change variations in the balloon will lead to a variation in the twist flow into this particular reserve area. In principle, the balloon being stable, the possibility of twist variation due to the variation in balloon shape is minimum. In comparison to the ring spinning, where the twisting and winding zones are small ones, and the area of contact of the yarn with the traveler and the balloon and to the apex of the thread guide is almost constant with negligible variation. We have seen that in the kind of normal doubler, the variation is very negligible. But in this case, where the path of the yarn is large, the variation at twist is controlled, and there is no chance in the conventional, there is no chance for the yarn to lose the twist due to its restricted controlled path between the starting and the twisting to the thread guide. This is all about conventional system. Whereas in the case of TFO twister, the yarn path is more, and this results in a longer path during the entire twisting operation. Now let us see the other parts that are there and the functions. The drop wire. The function of the drop wire is to stop the winding automatically as soon as the thread breaks. Waxing device and indication lamp. Downstream process requirement of waxed plied yarns can be met by installing waxing device. If the downstream process like knitting requires waxing of the yarn, then we can have a waxing device that is shown here. Special magnet holder ensures uniform wax application. Then we look at the indication lamps. Indication lamp glows in the event of yarn break on spindles. Differential lamp indication for left hand side and right hand side breaks for ease of identification of yarn break side. Also reduce reaction time and efficient operator patrolling to attend the breaks, thus lower spindle idle time. So these are the advantages of having indication lamps which glow and immediately indicate the breaks. We come to the bunching device. As required by downstream processes like warping, weaving, to enhance the running efficiency of the process, the bunching device can be installed to have reserve yarn at the tail end or at the base of the package. So winding head in the TFO, it looks like this. The plied and twisted yarn is wound on cones above the winding drum, forming one package per spindle located in the upper part of the machine. So this is known as the cradle. And cradle is a cone holder in the TFO to hold cones and enable smooth winding of the plied and twisted yarn on the cone. So this is how the cone is taken out from the machine for doffing. So type of drive, we can have two types of drives for this spindle of TFO. Tangential belt drive, using one single long belt to drive all the spindles through a centralized tensioning arrangement. We can also have a 4-spindle tape drive. Indigenous manufacturers largely use 4-spindle tape drive system, while almost the entire imported machines are with tangential belt drive system. So the 4 tape drive is shown here, where just like a ring frame, old conventional ring frames, you can have 4 spindles driven by this tape. And you can also have a spindle brake to stop the spindle when the yarn breaks, which is useful for knotting or piecing. So we come to the process sequences. These are the popular sequences. There is a ring spinning, then there is an auto winding, then there is a doubler winding, which will have this assembly wound package. Then it goes on the TFO. Then you have a conventional cone winding to remove if any faults are there, and then packaging. We can also have ring spinning. We can have ring spinning, then have go for auto winding to make a bigger package, then go for doubler winding to make a assembly package, then to TFO, and then without this conventional cone winding to remove any faults after TFO, directly it can go for packing. Then the third passage could be ring frame, then conventional cone winding. It could, instead of auto winding, you can have a doubler winding, TFO, conventional cone winding and package. Similarly, one can have ring spinning, conventional cone winding, doubler winding, TFO and packing. So this is taken from this particular reference here. An ideal feed package for TFO twister is parallel wound cylindrical package called cheese. In the doubler or the assembly winding process, 2 or more single yarns from cone are wound as cheese. This ensures equal tension on the feed yarns before entering into the twisting zone of TFO twister, and thereby enables proper twisting. If, however, two single end cheeses are directly used as feed packages in the TFO twister, corkscrewing may take place. This we have already seen in our earlier lecture. The rewinding after TFO may be done for the following requirement: to clear the package defects as well as yarn defects, more particularly untwisted yarns and knots, or to produce a spliced yarn instead of knots as demanded by some customer. That is, this particular winding after TFO is done for these two reasons, or to obtain even a compact package. Other sequences could be ring spinning, doubler winding, TFO, conventional cone winding, and packaging. Um, uh, so this could be another passage where you do not have auto winding or any kind of making the bigger package before having an assembly wound package. So the another passage could be ring spinning, doubler winding, TFO, and packaging, where you do not have um, cone winding later on to remove the faults. Another passage could be ring spinning, conventional cone winding, then doubler winding, TFO, and reeling, where we do not go for packaging, then or a large package or a cheese or a cone, and reeling is done and directly packed. Then we can have ring spinning, auto winding, doubler winding, TFO, which can then go for singeing, then conventional cone winding to remove faults, and then packaging. We can also have yarn from open end spinning, which is going on doubler winding, then TFO and packaging. We can, on the other hand, can have open end, conventional cone winding, doubler winding before this assembly wound, and then TFO and packing. And the last passage could be, instead of open end rotor yarn, we can have airjet yarn, which is MTS, and we can go for TFO and then directly for packaging. So these are the different process sequences that one can have. So advantages of TFO. Advantages are two turns with one spindle rotation, large knot-free yarn length, direct delivery of the twisted yarn on cones or cheeses, eliminating rewinding processes, twisting without rings and travelers, no deformed twister bobbins, no double threads, and higher production per spindle. Spindle speed is around 15,000 RPM. Possibility of getting hard, medium, and soft packages with less adjustment. Easier changeover from S type to Z type and vice versa. Twist per meter range is 157 to 2000. Possibility of twisting different yarn counts with same twist on the machine, and also increased loom shed efficiency, because if you have a good package, it will lead to downstream increase in efficiency in the downstream processes. Also low maintenance machine. And so with this, let us see a modern Technocorder TC2 by Sorer. So with this, we come to the end of this particular lecture on 241 twister. Thank you.